What if I told you that a tool, a really trusted tool that countless scientists use every single day, has a hidden flaw? And what if that flaw is giving them a dangerously false sense of confidence in their own results? Well, today we're going to pull back the curtain on a mistake that might be skewing studies all over the world.
Yeah, you heard that right. The very software that's supposed to help us find meaning in all this complex data could be, well, unintentionally leading us astray. It can make a scientific discovery seem way more certain than it actually is. So the big questions are, how is this even happening, and what can we do about it? All right, let's dive in.
Okay, so picture this. You've run an experiment and you've got this huge, massive list of all the tiny molecules, we call them metabolites, that were in your sample. This whole field is called metabolomics. And honestly, it's like someone just dumped a 1,000-piece puzzle on your table. Your job isn't just to count the pieces. It's to find out how they fit together to tell a story, a biological story. And scientists have a name for these stories. They call them pathways.
So how do you find these stories in all that chaos? Well, scientists have this really powerful tool called enrichment analysis. It's basically a statistical method that helps them see which of those biological pathways are the most active or the most important in their experiment. It works by checking if certain groups of molecules are showing up together way more often than you'd expect just by pure random chance.
All right, the most common type of this analysis is something called overrepresentation analysis, or just ORA for short. Now, the math behind it has a fancy name, hypergeometric probability, which sounds super intimidating, I know. But trust me, the actual idea is incredibly simple. We can break it all down with a classic analogy.
So let's imagine we have an urn, and it's filled with red and white balls. Think of the red balls as the metabolites that really changed in our experiment, the significant ones. The white balls, they're the ones that pretty much stay the same. Now, a biological pathway is kind of like reaching into that urn and pulling out a handful of balls. All ORA does is ask a simple question. What are the odds that we grab that many red balls in our handful just by dumb luck?
Okay, we can actually map this out visually in a simple 2x2 table. So in our urn, we've got 10 balls total. You can see that number down in the bottom right corner. 4 of those are red, are significant balls. Now, let's say we reach in and draw a handful of 6 balls. If you look at that top row, the drawn row, you'll see we got lucky. We pulled out all 4 red balls and 2 of the white ones. This table just organizes everything so we can ask that key question. What were the odds of that specific outcome happening purely by chance?
All right, let's leave the urn behind and look at some real data. This comes from an experiment on fasting mice. So now, instead of drawing balls, we're looking at metabolites that are in the glycolysis pathway. And just look at that top row. There are 9 metabolites in this pathway, and in our experiment, all 9 of them turned out to be significant. 0 were non-significant. I mean, that looks like a slam dunk, right? An incredibly strong signal.
So it all seems pretty straightforward and honestly pretty powerful. And it is, but here's the twist. There's a hidden, crucial mistake in how a lot of popular analysis tools apply this super simple test by default. It's a mistake that can totally warp the results.
So it all boils down to this one critical question. What happens when some of the metabolites just aren't detected at all? I mean, your machine couldn't even measure them. They weren't significant, they weren't non-significant, they were just absent, invisible. So how in the world are you supposed to count them?
Okay, now look at this. This table shows the exact same data we just looked at, but this time it's been run through a popular analysis tool using its default settings. Remember how our experiment had 282 total metabolites measured? Well, suddenly the analysis is telling us there are over 1,000. What? Where did hundreds and hundreds of extra data points just magically appear from?
And here it is. This is the big mistake. By default, these tools often take every single metabolite that exists in their massive database, but that you didn't actually detect in your experiment, and they just dump them all into the non-significant bucket. Think about that. It's treating things your machine couldn't even see as if you measured them and found they weren't important. This just massively inflates the numbers, especially that non-significant category.
And what this does is it creates this dangerous statistical illusion. See, when you blow up your sample size like that, even with totally irrelevant data, the math will almost always spit out a smaller, more impressive-looking p-value. And just like the research paper says, this makes a result seem way more significant than it actually is.
Okay, so that's the problem. How do we fix it? Well, the good news is, once you see the issue, the solutions are actually pretty logical. It really all comes down to being more honest about the data we actually have. So there are really two main paths forward here. The first one is the simple fix, something you can do right away. You just tell the software to use only the list of metabolites you actually detected in your experiment as the background universe. Simple. The second path is a bit more advanced, a better fix, where you use the data you do have to make an intelligent estimate about the significance of the data you're missing.
And this table, wow, this table just lays it all out perfectly. Now remember, in statistics, a smaller p-value usually means a more significant result. So just look at that first column, the flawed method. Those p-values are ridiculously tiny. They're screaming, this is a sure thing. But then, look what happens when we switch to the detected-only method. The p-values jump up. And check out the citric acid cycle. It goes from looking super significant to, well, not significant at all. And then that third column, the weighted estimate, gives us an even more nuanced, robust answer.
And this is such a critical point. A higher p-value isn't a worse result. It's a more honest result. It's a number that actually reflects your level of confidence based on the evidence you collected, not based on a giant database of things you never even measured in the first place.
You know, when you get right down to it, questioning these software defaults isn't just a nerdy statistics thing. It's about the integrity of science itself. Using better methods simply leads to better, more reliable, and more reproducible discoveries, period.
So, let's wrap this up with the key takeaways. First and most important, always question the default settings in your analysis tools. We've seen how just blindly trusting them can create a false sense of significance by misclassifying non-detected data. The simple fix? Use your own list of detected metabolites as the background. And if you want to take it a step further, remember there are even better, more advanced methods that can give you a more robust analysis.
And hey, for anyone out there who wants to put this into practice right away, there's actually a tool built for this. It's an R package called mseapca, and it's specifically designed to run these more accurate types of analysis, so you can sidestep this whole problem.
And all of this brings us to one last really important question. Look, this was just one default setting in one type of analysis. It really makes you wonder, doesn't it? What other hidden assumptions are buried in the defaults of all the other tools we rely on every single day? It's a good reminder that thinking critically about our tools is just as important as the experiment itself. Thanks for tuning in.